Panel members, come on up. I'm going to take James's lead and stay close to the water tables here. So, I want to say I'm really amazed at how accommodating Google has been here. You know, they let Dilip have PowerPoint for his presentation. They gave James a whole rainforest in South America, in the Amazon rainforest. So I thought that was very, very generous of you guys. Yeah, that's right. Well, you know, depends on how many computers you can find in the jungle. So we're going to talk about the local cooling solutions, and I'm going to take a little twist on that to make sure that we can cover all of our panel members. If we could have the next slide, we've got. I'm sorry, we've gone. We're going and let's go back one just to introduce everybody real quick. You've seen Joe up here 3 times already, I think, so you ought to know him by now. Andre Oppermann is the Chief Technology Officer of DeepGreen, which is a data center on a lake in Switzerland that he'll talk about, and that's what that first slide was. Bruno Michel is a researcher at IBM's labs here in Zurich, and Bruno is, if you have seen the children's show in the United States called Sesame Street, and one of these things doesn't quite fit, we'll see if we can get Bruno to fit into our local cooling solutions with a stretch of the definition a little bit. And then down on the end is my long-lost brother, Jeff Monroe, who is the Chief Executive Officer of Verne Global, who's going to talk to us about cloud computing in Iceland, which, since there's clouds over Iceland and most of Europe now. Oh, right. That's right. You just generate them and send them other places, right? So with that, I think we'll get, I had a few slides to introduce the topic, but basically what we're going to talk about is taking advantage of local resources that you find wherever they are in order to be able to improve the efficiency of the computing. And to stretch the definition of local a little bit, we're actually going to talk, Bruno's going to talk about localizing cooling right down to the heat source, so on-chip and even in-chip cooling inside supercomputing. And so we'll have some interesting discussion on that. So let's go to the next slide, and I think it's Andre's slide. We asked each of the panelists to prepare one slide. So naturally, I prepared 10, and Bruno got 7, I think, and then everybody else followed the rules. But we'll let Andre start with the talk about DeepGreen.
Okay, many thanks. The DeepGreen data center is a data center project which has received all permits in January this year. We are currently in the finalization of the detailed planning, and we'll start with construction later this year, to be finished about 12 months later. The unique thing here is that we are in the middle geographical center of Europe in Switzerland. The data center site is about 60 kilometers from here at the foot of the Alps. And we are going to use lake water from a very deep lake and cold lake to power or to cool our data center. It's actually the same approach as Google is doing in Finland. The advantage we have is that we can use sweet water. It's a very clean lake because it's fed from the snow that melts, and so in this way we have less trouble with fouling and all these kind of things, and filtering. This is one of the main parts there. The other thing we are doing is in the cooling area on the inside is to take the crack unit approach to the next level, because when we looked at it, we saw the traditional crack units are not very efficient, so they have constraints in size and with their heat exchange surface. So we redeveloped that into a sort of a cooling wall concept, where we have a hot aisle, we have a plenum, and take the air through the plenum and send it back through the heat exchangers, actually in the vertical, and send the air through it again. The advantage there is we have much more surface area, so we have a more efficient heat exchange, and we have less pressure drop on it. So our site, our data center is designed for a total capacity of 50 megawatts, 12,000 square meters net data center space. And when you look at it, a traditional cracked unit system at this size is about 2.7 megawatts for the internal air handling. And we bring it down to a little bit less than 900 kilowatts with this cooling wall concept. So that's quite an advantage, and I think that's also a place where many or lots of improvement can still be done in the data center space with the crack units. Well, after that, the entire cooling, that is the lake water pumps, the internal closed loop, and the air handling inside the data center halls adds up to about 3.5%. Which is almost nothing. So the electrical overheads, the UPS systems, we are a general purpose data center for the diverse IT loads of enterprises. So we have traditional UPS systems. So the electrical overhead, the losses in there actually dominate our PUE value, which is targeted at 1.1.
Great. Thanks, Andre. I think what we'll do is we'll go through all of the one slide presentations, and I should mention that Joe doesn't get any because he's already had 15 slides up here. So, and then we'll start. I have a few questions to get things started, and we really would like this to be interactive. So be thinking of your own questions about these issues. Let's go to the next slide, and this is the beginning of Bruno's presentation.
Okay, so what we want to implement is a zero-emission data center. And how is that going? By reusing the heat dissipated by a processor or a data center and doing space heating with that. We have shown that on the ETH building, so let's start with this slide. What we can do is save energy on cooling and save emission on the second user. And we do that for ETH, and that's what we can do now, but the switch to chip-size liquid cooling has other implications. So we will be able to shrink the computer. We want to shrink one rack into 1 cubic centimeter. Why do we want to do that? Because we spend a lot of energy on communication. The majority of the energy is spent on communication, not computation. So by shrinking a computer 1,000,000-fold, we will improve its efficiency by almost a factor of 100 in 15 years. Next slide. So, next slide. So, let's look at how we do computing now. We use a certain amount of energy to drive the IT. Then we use almost the same amount, let's say for the reverse data centers, to throw away the heat. For IBM, that means $500 million energy bill. We produce hot air for $500 million and throw it out of the window. So, and the message here, it doesn't have to be. But painting a data center green doesn't help. Right. So we need to change the basic physics in the data center. Next slide. In the past 20 years, we could rely on transistors becoming more efficient by making them smaller. This will stop. So we are at a difficult time because our main engine stops. We need a different engine to drive us forward, and this is the compaction engine. On the level of the system, not on the level of the transistors. The transistors have reached almost their limit. We need to work on another scale to be part of the solution to the climate. Next slide. So, please, next slide. Yes, the key here is water cooling. Water is 4,000 times more efficient for heat transport and has a 30 times higher thermal conductivity. Another good example. We have a processor. It's a 1 by 1 centimeter chip. It weighs 1 gram. The transistors that do all this job, including the wiring, the local wiring, weighs 1 milligram. We spend 1 kilogram for the cooler. We spend 1,000,000 times more mass and volume for the cooling than we do for the computation in the processor. So we want to change that. And this example is our own circulation system. You please can put forward twice. That will make things appear. Yeah. Okay, so our circulation system allows to do cooling, mass transport, but with a very low energy input. Our heart uses 5% of our metabolism. We spend 5% on mass transport. We want to do the same thing for data centers. Exactly same. PUE 1.05 plus the electrical delivery. Next slide. So we have shown that we can implement that based on a design that has been done for an air-cooled unit. We ripped off all the air cooling components and added a liquid cooling. And by that, we reduced the overall thermal resistance from the transistor to the mobile medium that transports the heat. In a data center, this is 75 degrees from the transistor to the cold air. In a water-cooled, high-performance water-cooled system where we have the processor directly cooled, we eliminate a lot of thermal resistances and make them smaller. That's the small boxes on the graph there. So we can capture the heat at the 60 degrees C temperature level without having the transistors run hotter. They're exactly at the same temperature. That's why the lifetime will be the same. So we don't want to affect the lifetime. With that approach, we can reduce the energy consumption to a considerable fraction, depending on the temperature outside, and we can heat houses. We can heat 700 homes, typical family homes, from a 10 megawatt data center. That's peak load. It would be more if it's band load. And there is a lot of distribution systems available in Europe that can distribute the heat. 6% of thermal demand of Europe is being transported with a district heating system, and the thermal demand in Europe is 30% of the carbon footprint. Data centers are 2%, so we have a 15 times larger market to selling to. So we want to change. In the past, we had paid cooling. Now everybody speaks from free cooling. Yeah. We want paying cooling.
Paying cooling, I love it.
So now, next slide. So we compared the design, an air-cooled design, with a high-performance cold water-cooled design and a hot water-cooled design. So the cold water design, high-performance cooling, reduces the processor temperature by 40 degrees compared to what it is in an air-cooled version. That reduces the energy consumption. That's good. It reduces energy consumption with constant fan speed at about 5%. That's the transistor physics. Now, if we increase the temperature back to the temperature it was in the air-cooled blade, we have the same processor temperature, 68 degrees, 60 degree coolant input, 8 degrees delta only between the coolant and the transistor. We have the same energy spent as in the air-cooled version, but we make a large fraction reusable. And that pays us money back, right? Because heat has a value if it exceeds a certain threshold. So we have to fight for each degree. If we reach 65 degrees, we get a lot of money back. And we showed that at the ETH30. Next slide. With the Akasar system. Now, our plans are by a year from now, have a 3 petaflop system built in Munich with hot water cooling. This system will be composed of about 20,000 nodes, 3 petaflop overall performance. It should be the #1 on the top 500 as well as on the green 500. Because we have a very low energy consumption, which is measured by the green 500. And in addition, we have 90% energy reuse. The PUE of the system, which is not most relevant for an energy reuse system, will be 1.1. We don't need any chillers, and we only need a water pump be driven by. And we have seen water pumps can be driven between 1% and 5% of energy. Yeah. We invest a little bit more of pumping power, as our heart does, because we can increase the heat transfer coefficient between the chip and the water by having a little bit more pressure drop and microfluidic capillaries. Next slide. So we look, of course, at value of heat in different climate. It works well in Finland. We have seen that. It works well, reasonably well also here. We can do space heating during 6 months of the year. That saves us some energy or reduces carbon footprint, not by 100%, but by a large fraction. In a hot climate, we have been thinking a long time. We can, of course, replace a lot of chiller energy in a hot climate, maybe 50% of the energy, 40% of the energy, somewhere around that. But nobody wants to heat. Now, we were looking, is there consumers of heat in a hot climate? Yes, there is. Desalination needs a lot in a dry climate. Yeah. And the second is we can convert heat into cold with a process known as adsorption chiller. And adsorption chillers, luckily, don't need too high temperature. They can live with 75 degree temperature, and that's our target for the next generation. Have about 65 to 75 degree output, so that we can produce cooling for a legacy part of our data center. As long as our hot water cooled components are 80% of the data center, we can cool the rest. So we don't need any external cooling, any electric cooling. Next slide. Now, future. we take the example of our brain. Our brain has an efficiency which is about 10,000 times higher than a computer. There was a big demonstration. Watson competed against humans.
Right.
Humans need 20 watts. Watson needs 200 kilowatts. 10,000 times more. 10 to 100,000 times more. So that's a large difference. And we want to change that. And the key is making distances smaller. And that is possible by stacking chips on top of each other. So instead of the main memory being 20 centimeters away from the processor, it's only 200 microns away from the processor, with a lot more connections allowed or enabled through silicon vias. Next slide. And the challenge here is thermal, because as we stack chips, we stack the number of heat fluxes, and we even add the thermal resistances. So beyond two processor, impossible. How do we want to solve that? Next slide. By having interlayer cooling. So we have cooling in between each layer or set of layers. So we can have one processor plus a few memory layers, and then a cooling layer. And we can remove 5 kilowatts out of a cubic centimeter. So one rack with all its power dissipation in 1 cubic centimeter, but this will be much higher performance, this processor, because all the distances are smaller. And we have demonstrated that on a cooling test vehicle, not as a processor, but on the cooling performance. And we are working on, of course, the whole industry is working on the through silicon vias to make that possible in a reasonable amount of time. Next slide. Okay, so the main message is we can save a lot of energy. We can do energy reuse by having direct chip cooling. And we have a roadmap for the next 15 years. That is enabled by the introduction of chip-level liquid cooling that allows a compaction of the computers by a large factor. So we save energy costs 2 to 3x with direct chip cooling, and we can increase the overall computation efficiency by almost a factor of 100 by going to this complexity. Next slide. So that we have a few paradigm change: the air to liquid cooling, the Moore's law going 3D and surviving some more years, and energy to be used more wisely, not throwing money out of the window in the future. Right. And by the way, this technology developed for the high-performance coolers can also help in solar concentrators and allow us to get the energy for our data centers more easily.
Fantastic.
Okay. And by the way, the picture is kind of strange here. That's our CEO presenting the 3D chip stack to Frau Merkel, German Chancellor. Ah. They're both happy. The German Chancellor is happy because she can save the planet, and our CEO because there is a business behind it.
Right, they'll make money. Fantastic. Thank you, Bruno. I appreciate that. And then finally, we'll have Jeff talk about Verne Green in Iceland. So,
well, first, the weather is really nice here. And for those of you attempting to get back to London, there's worse places to be stranded. Right? I think when we look at this, I think you always have to ask the question, what are you solving for? And I think, in the prior venture, DuPont Fabris Technology, as an example, we were solving for a customer base that was too large for co-location and too small to do it themselves. And as a result, that kind of led us to the infrastructure that we designed and the operations model that we set up back in 2002. And really looking back on it, we did some very innovative things electrically, and this kind of ties into the cooling aspect of the discussion, because on the electrical side, we think that a lot of the customers who would come in would see the lights on, they'd see a UPS, but they really were not sophisticated in understanding what was happening behind the scenes of that infrastructure. So we deployed isolated parallel systems, reduced redundancy levels, did a lot of creative things. But on the cooling side, we were relatively conventional. It was, chillers, heavy iron, very similar to what you would see. Efficient, still an efficient system, not tier 4 redundancy, et cetera, but really built for that problem that we were solving for. And in Iceland, the real problem that we're solving for is power. power availability, power price, power escalation, power price visibility, stability. That is really what we're solving for. And it just so happens, and as you can see from the map in the top corner, that Iceland, and we've got the Grímsvatn volcano that's going off now identified. Eyjafjallajökull is just about 100 meters to the west, which was much bigger than Grímsvatn, but it's an example of the energy that exists in Iceland. Just an abundance of energy, geothermal energy in Iceland. To draw it back to the cooling equation, what it really does to anybody who's done a TCO model, a very comprehensive TCO model, where you take all the factors in, your amortized capital cost, your operational cost, your server, recycles or refreshes, and you take all those things into account. What you find out is that if you're looking in London, where power is, say, 10 or 12 pence per kilowatt hour, there are solutions that make a lot of sense, some of them very exotic. Whereas when you go to an environment where power comparatively is almost negligible, the cost of power, it changes that equation radically. Because all of a sudden, and when that power source is 100% renewable, 100% renewable. So it all of a sudden, I think my CTO and I were doing some whiteboard sessions at first. We really were getting into it. There's an underground aquifer. We have, tons of water that we can utilize for cooling. A geothermal development is amazing. The climate is just really optimal, very moderate temperatures. We do just, pass-through cooling. Chillerless system, very similar in concept. However, the difference is as an end user, you can tolerate excursions, which I like the term excursion. Whereas for what we do, although most excursions that I've been on end up with a hangover, but right, yeah. So, but what we really like about it is that we don't have to have those excursions in Iceland. We can really offer something as a third-party provider that fits within that acceptable operating realm. So, for us, I think there are a lot of very exotic cooling methodologies that can be deployed in Iceland, but when you really boil it down and you really get to 100% renewable energy mix, and you have this optimal climate and this very inexpensive power, it really turns the TCO analysis on its head. And that's why, for us, it's a unique place in the world. It's a unique place, from the energy mix, from the climate, but also, you've got a very educated workforce, et cetera, et cetera. So there's a lot of great benefits there. And we just find it very unique, and events like, again, the activity that's going on there just underpins the amount of energy that's stored.
Great, thank you. So we'll skip the rest of these slides in order to keep the discussion going. But it seems to me that in each case that we've talked about, Joe, in the case where you have found a location that's on cold water, and Andre, where you have as well, and Jeff, your location is got serendipitous power, bubbling up out of the ground, literally. Were those things that you went looking for specifically when you were trying to figure out the data center locations? Did you look for a site that matched a certain profile so you could implement? Or did you, once you had selected a site and saw a few things, say, oh, this is a good place that we should go because it has 3 of the 5 elements that we were looking for in terms of building an efficient data center and solution?
Well, I'll pick that. Joe's probably got some really good input on this, just from because you really went through a site selection. I would love to take credit for the site in Iceland, but it really was it was picked by the U.S. military. It's a former NATO Allied command base. It was picked for a reason, and you have the insurance carriers to go through and give it highly protected status. So, we kind of, this was by default identified through that mechanism, but you probably have a more interesting story on the selection.
I think as Urs has said, site selection is an exercise in compromise because there's a litany of variables that you're trying to solve for. And you're not going to find any one site that is the perfect fit for everything. So we start out with some basics, like for instance, we want to provide an excellent user experience for our users, and so that gets you into a generalized geography of where you're looking for. And then you do look for sites that have infrastructure that could be reused, how quickly we can get in and get a new site up to speed in a location. You look at, of course, power as a big factor. And then you look at localized cooling opportunities and what you could do, because over the course of the lifetime of the data center, that's going to be a major component in your TCO, right? And so you take all these things into consideration, and then you've got interconnectivity, networking, and all the rest. And it really is, like I said, an exercise in compromise. So you wind up you're evaluating 5, 10 sites in parallel, and one falls out as the best choice that kind of fit the best of all those compromises.
Okay, for us it was a very sort of deliberate decision. We were looking for a place. We wanted to stay in Switzerland. That was the constraint. The next one was that we wanted to use lake source cooling for efficiency. And the third one was we wanted to have access to large amounts of power. And then we were looking at the opportunities in Switzerland. We have a few deep lakes which are suitable, and we were evaluating them for all these criteria, and this particular lake called Lake Wallensee stood out because it has some space or some industrial area next to it where we could build the data center, not too far from the shore, and it has a large number of high voltage lines going through, bringing the hydropower from the Alps into the sort of Midlands, where the population and the industry is, and we can tap into that. So it was really a very deliberate decision to go for these things.
So first it was a wide swath, and then narrowing it down to, as we talked about yesterday, there's maybe only 3 or 4 lakes in Switzerland that might have met your criteria.
Exactly. So what we need is a lake that is deep for the cold water. It must be large enough to have the capacity to be able to sink 50 megawatts, and also the power. And the particular problem we have here with the mountains is that many lakes have mountains next to it.
Yeah.
So it's very difficult to locate larger structures there. And in other places like here around Zürich and Lake of Zürich, obviously is prime real estate. So placing a large data center close by is very difficult. There's, for example, in the south of Switzerland, close to Italy, there's a new data center being built for the ETH. They're also using lake source cooling, but they have to build the pipes about 2 miles through urban area, which is very difficult and expensive.
And expensive is the key, I think, in that case, because everything is leading toward that lower TCO. Bruno, I was really interested in when you were talking. Most of the time, when we think of the heat that comes off of the data center as very low grade and not worth. It's very difficult to transport in some way to make it worthwhile. You actually are trying to increase the temperature of the heat coming off of increase the grade of the heat, if you will, the quality of the heat that's coming off of the chips. Is that right? I mean,
Yes.
You're up to 68 C.
So that's the key, because if you're only about 20 degrees C above ambient, then heat has not a high enough value to justify investments.
Right.
But if the gradient between the waste heat or the heat resource and the ambient is high enough, then you can invest.
Becomes much more valuable.
And of course, then for us, we try to have a general concept, so I can't speak about a local placement, but there is new criteria coming. We need still all the other components, low power cost and a cold climate, because we want to contribute to space heating, and we need a local network or a district heating system, where we can feed into, because it's best if the data center is one of the providers in a district heating system. You have other providers like wood-fired power stations or so. Then we can provide energy during an extended time, and the others can cover the peak. So that's the most interesting scheme.
Right.
And then your energy has really a quite high value. So there is tariffs. There is a organization called Euroheat and Cool, and they have certain tariffs for heat.
Yeah.
And the tariffs increase as you increase the temperature. So for 60 to 80 degrees C heat, that you can get sometimes half the money back that you pay for electricity because it's subsidized.
But the site selection part of what you were talking about is you have to have a consumer of that of whatever heat comes out close enough by that the heat is still valuable.
Yeah. So it is challenging to find such sites, but there is geographic maps available that also list heat demand, and we have to look at these, and that's a new criteria then. Yes, to really find then new locations for data.
And how low does that heat demand? And what's the lowest temperature that would be valuable for exhaust heat? I mean, suppose we had an air cooling system that was exhausting at 31 or 35.
I said there is a 15 times higher demand for heat than data centers dissipate overall, or ITC dissipates overall. If you have only ambient plus 20. Your demand is tiny.
Very low because
it's luck. It's a matter of luck.
A luck.
But as you go higher, then you can fulfill. You can satisfy maybe 50% of the overall demand.
Yeah,
that's the goal. That's the target.
Huh. So, and questions from the audience are welcome. If anybody has some, just raise your hand. We'll have someone come around with a mic. While we're getting set for that, let me ask you about the permitting process, because it seems to me that anytime you're going to start injecting heat into the environment, there's going to be some local authority who's going to have something to say about that. So all three of you data center folks, you must have gone through that, in the appealing to local authorities and getting through that. What was that process like?
Well, they all have something to say about that. In our experience in Finland, using seawater cooling for industry is very commonplace. As a matter of fact, one of the questions that I got most often was, why are you bothering building a tempering station or a tempering building for the reject water? Because the other industries here reject water at a much higher temperature anyhow. And so, but that was important in our value system, and so that was a choice that we made consciously. But they in other cases, certainly the authorities are always interested in what are you going to be doing that's going to have a potential impact on the local environment. And so really I think that the best way is to go there with a lot of information about as much detail as you can with what you're planning, what your temperatures are going to be, and what you're going to do to mitigate that right up front, and do it in a kind of a partnership manner, in a transparent way, and then they get a better comfort with, okay, I understand what they're thinking. Now let's see if this fits in with our regulations or not.
Yeah, I can only say most of the same. Again, be prepared. Have your numbers and figures ready. We had to do some studies how to bring the heated water back into the lake to prevent changes to the environment locally. So in this particular case, we feed back the hot water at depths of 30 meters, which is way below the biological active zone in this particular lake. And also we have at the exhaust of this pipe, we have a sort of a mixing system that takes cold water from the surrounding area and sort of mixes it already. So we don't have a too great temperature difference there. Other than that, in general, lake water usage is quite popular in Switzerland. So, for example, around here, Lake of Zürich, many buildings are heated and cooled by lake water. So that's quite common. Actually, it's sort of already a requirement. So we have regulations and laws that say you have to be energy efficient. So it has a certain level you must reach, and you should be better. And the authorities always say, okay, you can do better. Try, just try it. So you're not going to agree to the just the minimum requirements.
Right. And Jeff, did you have, I mean, your site had already been identified and was already a military base. Did it have some sort of special permitting already available to make it for you?
Well, I have to say that after, Iceland's a unique situation. After negotiating with the Icelandic government on VAT taxation policy reform, which they finally did pass and get straight, the other stuff has been relatively straightforward. I would echo similar sentiments that the most effective approach is always to go in and be very transparent and really bring the local authority into the process and make them part of the solution.
Right.
But with Iceland's unique community, you've got a lot of aluminum smelters up there, and they're, the aluminum smelters, they do bad things to the landscape, right? I mean, there's sludge that they throw off, and so I think that Reykjanesbær, which is the peninsula of southwest Iceland that we're on, they really look at data centers as a savior for their economy, a wonder, and it's a perfect fit. And don't forget that Iceland, they invested a tremendous amount of money in multi-terabit, multi-redundant cable systems to connect the country that are about 0.5% utilized or something. So they're very motivated in that process, as opposed to going in and having people who are very forceful in trying to compartmentalize what you want to do or stifle your innovation.
So what you're saying is, find someone who looks much worse than you and put yourself right next to them as part of your site selection criteria.
Absolutely. This is very effective.
That makes a lot of sense,
Mark,
I think. Did I see we had a question? Yeah, we have a question up here.
Question for Jeff. You had a statistic up there that about 25% of your energy in Iceland was geothermal. Could you give us a brief overview of the kind of capex costs and the running costs and the payback period of geothermal energy?
Well, I tell you, so from a cost perspective, obviously, that's something that we won't typically disclose what our deals are, what we've negotiated, or what we see in the marketplace. But I will say that, an order of magnitude basis, the mix of geothermal and hydroelectric energy for high intensive users within Iceland is a fraction of the cost in the UK or in London. So London's running 10 to 14 pence per kilowatt hour depending upon the region you're in, and I mean Iceland it's literally the high intensity users are a fraction of that, and it's primarily driven by, I'll kind of touch on the geothermal piece. It's primarily driven by the fact that you've got a population of 320,000 people, yet you have a very, very robust electrical grid and and a generation system that supplies the aluminum smelters. So it's the opposite of what you see in tier 1 cities, where you've got this electrical load that fluctuates based upon people going to work, people going home, and really very suboptimal places for data centers to be located. So, and the grid is young. It just has a very, very efficient operating history relative to other grids in developed countries. So, from a geothermal standpoint, what we really like about that, so think about hydroelectric. These are 400 plus megawatt plants, and they're difficult to get permitted within Iceland. They're difficult to get built. They're very time consuming, and they always require a smelter or a large user to anchor that capital investment. So geothermal is really attractive because, and going to a geothermal plant is just incredible, an incredible experience to see how efficient these things are, how clean they are, and how good the Icelanders are at geothermal energy. But these things can be deployed in 50 megawatt chunks or 35 megawatt chunks, and so it's much more incremental development, and which is very nicely matched to a data center, as opposed to kind of going up there and you start to expand and grow, and you hope they put another 400 megawatt hydro plant in. And so, the Icelanders are used to the, one big switch, you turn it on, it's a big hydro plant. Geothermal is much better suited to the thousands of switches that we have in a data center that kind of turn on over time.
And then I think Ian had a question.
Yeah, it's for Joe and Andre, actually. If you were starting again and you're looking at the new ASHRAE standards for server inlet temperature, you're both in areas of clean air and cool temperatures. Why would you bother going for lake and harbour cooling?
Well, the thing with the lake is that it's more energy efficient, because when you have you're talking about fresh air cooling or just economize?
Straight fresh air
Straight
in
fresh-
and heat out.
The thing is, when you look at it, the filtering that has to be done, even in reasonable clean air, the pressure drop you have on the filters is quite high. So you need lots of fan power to overcome that. And if you look at our energy setup with the lake water pumps, we are better than that. And also the filters, you have to exchange the filters all the time, because you're pushing so much air through it, and so much pollution is being held back there. It's a total cost of ownership issue, and we are faring much better with the lake water usage there. And we always have the controlled temperature, so there's no variation. So no stress on the equipment, always the same humidity, always the same temperature, just perfectly suited for general purpose IT environments.
I can add something in support of that. Transporting a compressible medium like air takes 10 times as much energy as an incompressible medium like water. That's the physics behind it.
So first of all, I'd like to say that I love all forms of free cooling. So I'm not picking any of my babies over the other ones. I love all my data centers equally. But really, I mentioned earlier that because we do have the salt water and the salt in the air to deal with, even though the Gulf of Finland is brackish and not really heavily high salinity content, but still that was a concern with free air cooling. And then the other thing is that there was a tremendous amount of the existing infrastructure there that was already being used for seawater cooling. So a lot of variables kind of came together that said this makes sense for this specific location at this time with the amount that we could reuse and whatnot. So it wasn't that it was entirely out of the question, but economically this was more advantageous.
Other questions from the audience? Yeah. Back to our question row.
Yeah, we've got to keep the stats up
Yeah.
here on the row. I have two questions, if that's okay. One to Bruno and one to Andre. On Bruno, for Bruno, I was just wondering on the chip side, I was actually in, of all places, in Medellin, Colombia, which is not known for this, but for something else that Escobar was promoting a lot larger economy than anybody here. But they do have a group there that is a guy there that's doing some a PhD on using the actual chip itself as an evaporator and using basically a DX loop, and that gives you the advantage that you can compress that gas. So basically turning it into an evaporator. We looked at some issues on reducing the size, the surface tension to reduce the size of the bubble that comes out, etc. Have you guys done anything like that?
Yes. So we have done for the Akasar, we have done single-phase liquid cooling with water. For another research system, we have used a refrigerant, which is then being evaporated on the chip. The process is known as flow boiling, so we have to make sure that we don't evaporate everything, otherwise you have dry out and overheating. So it needs to be carefully controlled. We need to carefully control system pressure and flow rate, and then we can transport the same amount of power density out of the chip and even out of the chip stack. And we can condense then the refrigerant and reject the heat as normal, or we could add a slight compression to lift the output heat slightly, to increase its value. But we have to do that, of course, at the expense of energy. And we need to carefully analyze that, whether it's worth it or not. Normally in Carnot terms, it's not worth it, but if there is a demand just next to us that would be filled with 5 degrees more, then it pays. So, but such a system is much more expensive than a single-phase water-cooled system.
And that's why you chose to go water-cooled. And then for Andre, the interest is in the cooling wall that you have versus the cracks. Can you elaborate on that? Did you do that design yourself? Is that a commercially available product?
We didn't do the design ourselves. It's a commercially available product. It's a Swiss company that invented this. The company is called Mount Air. It's in a It's in a town called Kreuzlingen. So you can send me an email if you want to contact there. It has been put into production already in at least one site I was able to visit, and that convinced me. It's a site in London, also running on free cooling. And the thing there is they can run with very small delta T, so they can extend the free cooling period a lot, because in London the summer is not too hot.
Right, and does the fan integrate into the whole thing? So you've got the fan and the heat exchanger together?
Yes, it's sort of it's like a module you get. So it has the heat exchanger, it has the fans, and it has filters.
And lower pressure drop, I'm assuming across the coil, and you can go lower velocities, which give you a better approach.
Yes, so you don't get beyond 2 meters per second.
Great, thank you.
Nice gentle breeze. How much extra engineering did you have to do for these sites in order to take advantage of the local resources? I mean, we heard, I think it was Brian from Norman Disney Young talk about that. He said it was like 11% for extra infrastructure. Is there, I mean, when you pick a unique site and you have to do unique engineering, doesn't that add to the total cost of the project? And I understand that it's paying off further down, but you can't really reuse your paper plant site, or maybe you can, because there's a lot of paper plants in Finland that are available now, I hear. But I mean, is there how much, roughly what's the order of magnitude of the extra expense per project?
So I'm trying to get a real good estimate here, but I think that I mentioned earlier that I'm not sure that the economics would be entirely viable for a smaller site, because the upfront engineering and modeling that we did to ensure that this was going to be a good cost of operations decision for the long term. We spent quite a bit of time, so that upfront non-recurring engineering cost amortized over a larger data center makes more sense, something that you're going to be running for many, many years. But if it were, a small site, it may not make sense. But order of magnitude, it would be hard to give you an exact estimate, but it would probably be at least in the 15-20% range of extra upfront non-recurring engineering type costs.
Yeah, for us, because lake source cooling is common in Switzerland, not for data centers but for normal heating and cooling uses. There's is a lot of knowledge available. In particular, the lake we selected is one of the main potable water supplies for Zürich. So there's a large amount of data available on that lake, done by the local water authorities. They're monitoring it for like 40 years now. So we could really draw on this data and make and come to a clear conclusion, like you had some data available from Finland. And the other thing is, if you look at it from a capital expenditure perspective, of course you have a higher upfront cost in building all these pipes and everything, and the underwater works that have to be done. But if I compare it to a more traditional solution with a free cooling system and a compressor, a mechanical cooling system, then we are saving a considerable amount of money there, not only in operation but also in installations. And to capture the peaks, we would have to add another 11 megawatts of power to run the infrastructure. So we can do it now with some 250 kilowatts. So that's enormous savings, and that's also one of our competitive advantages we have there, because our cost is much lower. So we can give you better prices on the data center.
Same service.
And also we are in the heart of Europe, so we have very low latency to the majority of the population here.
Right. How about you, Jeff? You have a feel for extra engineering cost or?
I have to say that probably what you guys experience in Finland is unique, right? I mean, that's a pretty unique setup to use seawater and have those existing, aqueducts that you have to go through and research. And it sounded like there was some interesting engineering on the fiberglass piping and the analysis of the seawater temperature. And so I think, that's a unique situation for us. What we do is we do the design charrettes. We come up with the design scheme, and then we found the engineering in Iceland to be exceptionally good. I mean, they're used to designing smelters, and these are big, heavy industrial facilities. But also, I think that our infrastructure there is much more straightforward. It's not exotic. It's we do have the aquifer, we can use it, but we're in an environment with 100% renewable, abundant energy and an optimized climate, and it just kind of
Might as well use electrical.
well, again, you plug it into the TCO analysis and you look at it and you kind of say, across the board that, again, if you're not doing something really exotic, then, you really don't see that substantial cost impact.
Yeah, one of the things that was a little bit unique on the mindset that we had to work with was for most of the seawater cooling industry that was up there, they routinely take like annual or semi-annual shutdowns to do major maintenance on their plants. So we had to, of course, think about this being, the traditional 7x24 by forever type model, right? And not planning for any major maintenance activities. And that was different. That was something that they were not used to, because whether it was a power plant or a pulp and paper mill, they're used to being able to say, okay, at certain times of the year, we just have scheduled shutdowns. We're going to do our major maintenance then. So that was, a mindset that we had to kind of get over with the local engineering teams there.
Bruno, did you?
So concerning cost on node level cooling, we have to assume about 10% cost added to such a node. But on the other hand, we can save then on the facility. So more or less this balances out, but if you analyze the data center on the total cost of ownership, you have a very short payback for this added investment.
And when you say that, where does that 10% come from? Is that in the actual chip,
plumbing.
or is it the plumbing? But
the micro-channel heat exchanger and the plumbing.
Yeah.
And for an implementation, if somebody wants to implement that, it requires a certain minimum size, because you need to have an additional piping in a data center, and that would be of the order of 10 racks size.
10 racks of
of course, the
AquaSite.
SuperMOOC is 200 racks, so there it really
You're
makes
okay
sense.
on the minimum there. Yeah. Any more questions from the audience? I didn't see any yet. Bruno, so you said the first implementation of this is going to be a supercomputer that's going to hit the top of the top 500, the top of the green 500. Do you see this moving into enterprise computing in the next decade, 100 years? How soon will there be?
So, so the SuperMOOC should be online in second quarter next year, and in second quarter next year it will be commercially available also as a commercial system, as a general purpose computing, because it's based on a general purpose processor.
What
an Intel
operating
processor.
system will it run? Windows?
normal
Will Windows run it?
Yes.
Super? Wow. That'll be amazing. I can't wait to do my email on that computer. That'll be. So that brings up the question then of, if we're taking advantage of liquid cooling in many of these places, and I guess we're not, more or less we're conventional except for Bruno's solution, which is liquid all the way into the chip. Do you see the need for special compensation or special taking advantage of those things in the design center, getting fluid all the way into there? Someone here was up here earlier and said, I think it was Rob said, customers don't want water in the data center at all, in a co-location facility. You don't have that problem because you're taking advantage of the outside, but Bruno, do you think that that's going to be an issue with?
So of course, this statement we always hear. Our first answer is, of course, data center computer room air conditioners were always water driven, so water has been in the data center all the time.
For all the time.
It has been 20 years back in the high performance mainframes, and now it's approaching slowly to the rear door. Nobody has any objections with water in a in-row cooler or whatever it's called, and now we make the next step into a module and onto the chip. But we use the same technology. It has been proven to work for computers that ran many years with water cooling.
Right.
Yeah, I would say our data center, we don't build it for yesterday, we don't build it for today, we build it for tomorrow. So we anticipated that one day we will have water-cooled CPU or computers. So we have put all the basic infrastructure in place so that we can connect additional heat exchangers with different temperature levels and everything to support these new kinds of systems.
Interesting. How Jeff, what stage are you guys at in developing the Verne Global?
Well, we've got the underlying power infrastructure complete, and we are in development, currently in development on our first, what we're calling our first module, which will be just about 1 megawatt. And we're going to have an announcement that'll be out shortly, so I don't want to jump ahead of that. But we're in development, and we're, again, the cooling methodology that we're using is open air cooling. This is, it is just an optimal climate for it. However, we have definitely been talking to people that want to take advantage of the underground aquifer. So I mean, I think to Bruno's point, you're going to find people for whatever they're driving, higher density, eking out the last little bit of efficiency. But again, we do everything by TCO, right? I mean, everything that we do is a holistic approach, because all of these things are connected together as you move that dial around.
And it's easier to get system admins in Iceland than it is in Alert, Canada, wherever that was.
You just reminded me of something. You just reminded me of something, which is I'm not allowed back into Iceland. I have to find 3 of the most beautiful women in the city here and bring them back with me. Oh. Because that's a Viking tradition. If you guys don't know, so
well, you don't have to worry about getting back to Iceland anyway.
Two of the investors said, "Don't come back." Right.
Bruno, I'm sorry that Dean Nelson isn't here still because he has this penchant for density, and
Yes.
we talked about the density of the computer, the 3D chip that you were going to. You said it was 5 kilowatts per
cubic centimeter.
Per cubic
That's the
centimeter.
ultimate limit you can transport with fluid, with water. And density is really key. It starts with a data center. The smaller you build your data center, the more efficient it becomes, and
Right.
the cheaper it becomes. And our goal is to make computers as dense as our brain. So currently, a computer is about 10 million times less dense than a brain. And we want to bridge that. And our assumption is that once it is as dense as our brain, it's also as efficient as our brain.
But arguably, for most parts, I mean, except for maybe some very, very highly populated areas in New York City or maybe here in Zurich, isn't building the white space the least expensive component and the power and cooling infrastructure the most expensive component? So if you have 5 kW per square centimeter, you still have to build the power infrastructure, and your cooling is arguably a little bit more expensive on your overhead. Why is it so important to have that extreme density?
Through the compression, we increase the efficiency. You need to supply 100 times less power for the same compute power performance. So it's all about efficiency. In the past, everybody analyzed the system based on performance. In the future, everybody will analyze the system based on efficiency, and that's a different point.
Well, and you and I talked offline about how the power, and you mentioned that 99% of the power
Is
that's
communication.
flying around the computer is to
if
move
we
information towards the
radically
processor.
analyze a computer, where does the power go
Yeah.
that you feed to the
Right.
system,
Right.
then it goes to the majority into shuttling bits around and not into doing a register multiplication. So at the processor, let's say, we are still working with a design that looks similar to a PCAT. The processor has become 10,000 times better. The board, the system, only is 100 times better. There is a gap. And we are just adding crutches. We are adding little, we are
incremental
yeah.
improvements rather
so,
than radical
so we need
ones.
to radically change how we build computers in the future. There is a paradigm change imminent
Yeah.
now.
Interesting. Fellow.
Yeah, just to further that comment, I'm going to hand the mic over here to one of your fellows. To Joe's point, I think one is making it more efficient, but the other is the big thing of, as we had a discussion earlier, Bruno, about entropy or exergy questions. It's being able to reutilize that energy in secondary processes. And if you let the energy dissipate into the air, you're never going to have enough delta and temperature difference to reutilize that in a secondary process. I think that's where Bruno's going, and I think his colleague here is going to comment on something.
So we'll have a conversation between the two IBM researchers. So if you have to check your email, this would be the time to do it. No, sorry, Ronald, go ahead.
So no, this is Ronald. So I think that as a remark, when Seymour Cray did his first large machine, he actually did exactly the same. He made the existing machine just much smaller. That resulted in this nice-looking machine that he did 30 years ago. And when you look at the original keynote that he did at the first supercomputing, all of the remarks that he makes at that time are still applicable today. It is worth watching. Now, talking about efficiency, I completely agree that the new metric is efficiency and much less performance on a per core, on a per thread basis. Also given the fact that workloads are changing. So the first remark that I would like to make is that I think that this conference has made a really good point in there's a whole bunch of low-hanging fruit that allows us to go from PUEs of 2.5 to somewhere close over 1 by doing what I would say smart engineering and just optimizing the system. But I just have to remind you, this is a one-time gain. You can only do this once. It's not scalable, not a repeatable thing, such that as we've had with Moore's Law and with CMOS over the past, say, 30 years. And so I completely agree with Bruno's vision that the real issue that we have is the data transport, because this is where the energy is used. If you do an analysis on where the energy is spent in the servers, 1% is spent on compute. 1% is spent on compute. 99% is spent on data motion. That's where the energy goes. And so my personal interest is to say, it's great that you work on, on the PUE above 1. I want to work on the PUE below 1, because this is where most of the data or most of the advantage can be made. And the key thing here is that we need a holistic optimization of the algorithms, the applications on the architecture of the machine.
Right.
I completely agree with Bruno to say we need to make this smaller. We have a need and an opportunity there to do that, but nobody knows how to do that. And the start is at the application.
The applications. And the only thing I'll add to your comment is that we've gotten a somewhat skewed viewpoint by the participants that we've had today, because the companies that have talked about it are so good at this. I think it was Urs who put up the statistic early in the presentation that said that there are 7.5 million data centers in the world, and a very small percentage of them are on lakes or bays or owned by the companies that have been presenting today. And I think there's a huge opportunity to reduce energy consumption. The one-time trick, as you say, but there are a million of them out there, so we can do it over and over again. Ian.
Yeah, can I illustrate something why we should listen very, very carefully to what Bruno says? And this is from our recent past. If you go back only to 1997, there was a scientific establishment in the States, Scandia Labs, and they broke the world record with a supercomputer. They hit 1.8 teraflops of computing, number crunching, 1.8 million floating operations per second. They took 800 kilowatts to do it. It took 200 square meters to do it. Only 9 years later, 2006, it was actually exceeded by a Sony PlayStation.
Yeah.
A Sony PlayStation did it with 200 watts, doesn't need air conditioning, and could be dropped by children. Yeah. Now, if you think that's only in our recent past, how on earth can we even suggest that what Bruno is talking about is future thinking? You asked the question, in 10 years. Yeah. His immediate answer was, well, next year it'll be a product.
Right.
Yeah.
Right.
So 3 years' time,
That's a good point.
you won't get that 1 cubic centimeter in the keyboard. Yeah. It only needs the escape key.
5 kilowatts.
The whole thing can be in a 5 kilowatt escape key. And we can go back to the Control-Alt-Delete days,
Right. Sorry. So, any other questions from the audience? How are we doing on time? We're got a couple more minutes, yeah? Or if you had enough of us up here, I think that there's a reception waiting for us, right? So, yeah. Oh man, I'm wrapping it up here. Then it's without any more questions, I want to thank our panelists for being up here. Great insights, and congratulations on your highly efficient design.